Welcome back. In this present lecture, we will discuss about numerical problems on Thevenin's theorem. In the last lecture, we have seen the statement of Thevenin's theorem, and we have also seen the explanation regarding the Thevenin's theorem, and we have done some example problems on Thevenin's theorem. In this lecture, we will solve problems on Thevenin's theorem, and I hope that by the end of this lecture, you will be able to determine Thevenin's equivalent of a given circuit. Before I go with this numerical problems on Thevenin's theorem, you know that any network can be replaced by a voltage source in series with a resistance. The voltage source is the open circuit voltage across the terminals, whereas Rs, which is nothing but your Thevenin's equivalent resistance, it is the equivalent resistance seen through the terminals. Okay, so coming back to determining the Thevenin's equivalent, you know that I have listed you 5 steps. The first step is remove the elements and ensure that it is open circuited, the terminals are open. This is your first step. Second step is determine the VTH using nodal analysis or mesh analysis. And step number 3 is replace all the independent sources. Step number 4 is determining RTH. And step number 5, replace this VTH in series with your RTH. These are the 5 steps. So a quick review. Step number 1 is about removing that load resistance. Step number 2 is about determining VTH. Step number 3 is replacing the sources. Step number 4 is determining equivalent resistance. Step number 5 is replacing the network with the Thevenin's equivalent circuits. Now, coming to the numerical problem on Thevenin's theorem. Now, this is the problem which is given for you. You need to obtain the Thevenin's equivalent of the circuit of the figure which has been given here at terminals A and B. So it is already open circuited. So you need to determine the voltage across this VTH, which we call it as Thevenin's voltage, and the other one is Thevenin's resistance across these two terminals. And they are also asking you to determine the current through the load resistance if RL is equal to 3 ohms. So first of all, let us determine the Thevenin's equivalent of the circuit. You know that we have 5 steps. The first step is open circuiting the terminals. Number 2 is determining VTH. Number 3 is replace sources. Number 4 is RTH. And number 5 is network replacing. Right? So we will start with this one. We will start with the step number 1. You see that step number 1, already the terminals A and B are open circuited. So there is no change in the circuit. So I have drawn the same circuit again here. Whereas coming to step number 2 is about determining the Thevenin's voltage. We call it as an open circuit voltage across the terminals A and B. Right. So you can apply nodal analysis for this one. So when we do apply nodal analysis for this one, you can see that there are 2 effective nodes. See, this is 0, so this will be 0. I'll take this one as 0. This is also 0, and this is also 0. If this is 0, then this will become minus 48, and this will become 1, and this will become another one. Both are same, right? And yeah, you can take this entire one as 6 ohms if you want. Okay, or else you can go with another node also, choices, yes. See here, what I'm doing is I'm taking these two resistance as 6 ohms combinedly. So I'm just replacing the network. So here I'll be taking as 6 ohms. And here I do have 6 amperes. And here I do have 12 ohms. And this is my A, this is my B, and this is my 12 ohms. And this is my 4 ohms resistor. And this is my 48 volts voltage source. So this I'm taking it as 0, this is minus 48, and this is 0, this is 0, this is 0, this is 0. So here I'll take it as VA, and here it is VB. Okay, see now, when I start applying KCL at this effective node VA, see it has 3 paths. This is first path, this is second path, this is third path, and this is fourth path, right? In the first path, you can see VA minus 0, this is VA minus 0 by 6. The second path is directly having a current source, so I'll take it as minus 6 because it is incoming. The third path is VA minus 0 by the resistance is 12. And the fourth path is open circuited, so no current will be flowing. So this is my effective equation. If I solve this, I'll be getting VA is equal to 24. Now, similarly, if I write the equation at effective node B, here there are 3 paths. First path, it is open circuited, 0. Second path, it is VB to 0, VB minus 0 by 12. Third path is VB minus of minus 48 by 4. See, VB, I am taking this one as VB. 3 paths, no current here. In this one, VB to 0, VB minus 0 by 12. This is the third path. Since it is 0, it is minus 48. VB minus of minus 48 by 12. If I solve this one, I'll be getting VB is equal to minus 36. Which means that this voltage is 24 and this voltage is minus 36. So what is VAB? VAB is what my VTH is equal to VA minus VB, which is equal to 24 minus of minus 36. That is 60 volts. Okay. Now, so the second step is completed. So now moving on to step number 3. Now we are supposed to replace all the sources with internal resistance in this circuit. Here you can see there is a voltage source and there is a current source here. Voltage source ideally will be short circuited, whereas current source will be open circuited, right? So I am open circuiting this one, see here, and I am short circuiting this one. So I am short circuiting. So this is my equivalent resistance. If you carefully see, don't get confused. If I start my current here, I must get it back here. So I can have in this way, or I can have in this way, and it will join, it will go in this way, or the current may go in this way. These are the possible ways. So what is the best thing which I can do here? See, if the current is going in this way, I can take it as the same current is flowing these two. So I'll take it as 6 ohms in parallel with, see, I'll replace it. 4 and 2 are in series, right? So I'll take it as 6 ohms, right? And this is already 12 ohms. Here it is 12 ohms. And here it is 4 ohms. If you carefully see, again these two are in parallel. So 6 into 12 by 6 plus 12. Here also these two are in parallel. 12 into 4 by 12 plus 4. This is 3, whereas this is 4. So now I'll replace this entire one with 4 ohms. I'll replace this entire one with 3 ohms. So this is my network, 4 and 3. Now if you carefully see, these both are in series. So I'll take it as 4 plus 3 is equal to 7 ohms. So RTH is equal to 7 ohms. Okay. So this is the way how we determine the VTH and RTH. So VTH we have obtained as 60 volts, RTH is 7 ohms. Now the final step is drawing the equivalent circuit, which means that this entire circuit now can be replaced by a voltage source 60 volts in series with the 7 ohms, the Thevenin's resistance. Now if you want to replace it here with your 3 ohms resistor, now what is the total current in the circuit? No, the total voltage is 60 by the total resistance is 7 plus 3. So the current will be 6 amperes. Okay. If you want to determine the voltage drop across this 3 ohms resistor, now what is the current through it? It is 6. And what is the voltage resistance? 6 3s are 18 volts. Like this you can do simple calculations. Okay. So I hope that now you are able to determine the Thevenin's equivalent of a given circuit. So this is your homework problem. See, using Thevenin's theorem, you are supposed to determine the potential drop across the 10 ohms resistor which is available here. Okay, the first step is open the terminals. So you keep them as A and B, and next you determine VTH, and then you determine the RTH, and finally replace it with the network. Okay. So we'll solve more problems in the class. Come prepared for the class, recording the Thevenin's theorem and practice all the problems.